Okay, so now we want to look at a little more involved circular motion problem. And we want to look at the bank turn problem. So we have a car here. You're looking at the rear end of the car. Here are the tires here. The car's going into the page right here. But it's making a turn, so it's kind of going around in a circle like this. And the radius of the circle right there is big R. So again, this is a bank. They're looking at the rear end of the car, and it's kind of going around. It's going around like this right here. Okay, and so what we want to do is, let's say we're given the coefficient of static friction. This is, even though the car is moving, it's not slipping right here. The tires aren't sliding on here. They're so we can consider this the mu s right here. Just because you're moving, rolling, doesn't mean you're slipping right here. There's no slipping going on. And we're given this theta, and we want to find what's the maximum speed you can go around this bank turn. And also, if this is really steep, what's the minimum speed? Because if you go too slow, you're going to slide down this way. If you go too fast, you're going to want to slide out that way. Okay, so those are the two speeds we want to find. So again, draw the picture. There's our picture. Draw the forces. We have mg coming straight down. We're going to first look at the case where we're going too fast. If we're going as fast as possible, the car wants to slide out, the friction would be in this direction, right? It wants to fight the slippage. The normal force comes up, again, perpendicular to the surface through the object. So those are the only three forces we have right here. Now, to put the coordinate system in, I don't want to put a coordinate system tilted, because the acceleration is actually this way. That's the center of the circle right here. The center of the circle is right there. So we want to put one of our axes towards the center of the circle. So I'm going to put my axes in this direction. So that means I have to break the friction into its components and the normal, not the mg. The mg is just straight down. I don't want to draw that force here, but I drew it over here. The frictional force is right here. Since that angle's theta, this angle's theta, something about two parallel lines and a line going through it. These two are the same angle. So if that's theta, this is the adjacent side, so that's the frictional force cosine theta. This side is the opposite. I'll draw it over here. That's the frictional force sine. So that friction breaks down into these two. The normal over here, since this angle is theta, and this line are perpendicular, that angle is 90 minus theta. This red line and that red line are perpendicular, so that's 90 minus theta. That's back to theta again. So these two are the same angle. So now we have the normal force, and we have it going out in that direction, and the angle theta is here. So this is the adjacent side, so that's n cosine theta. The opposite side across the top, which I draw down there, is n sine theta. So these two forces will replace that one, and these two forces will replace this one. Okay, so now we can write out the sum of the force equations right here. The force is inward. This is inward direction right here. We've got the n sine theta, which is this one, and we got the frictional force cosine theta. So those are the only two forces inward, and since we're going in a circle, we set it equal to mv squared over r. If we look at the forces in the vertical direction, the upward, which is n cosine theta, minus the downward, we have the frictional force sine, and we have mg. So we have n cosine minus frictional force sine minus mg equals 0. Okay, and then we also have, this is static friction. Frictional force, remember, is normally less than or equal to, but we're on the verge of slipping. We want to calculate the maximum speed. So we set this equal. And at the same time, our v becomes v max because we're going as fast as possible. So I'm just going to, now I can just plug this mu s n into both of these two places and rewrite them again. So the top equation is n sine theta plus, and now we're plugging in our friction, which is mu s n cosine theta equals mv squared over r. Now v is max because we're looking at the max case. And then here's the lower equation, n cosine theta minus, we plug in that for friction, mu s n sine theta, and that, put the mg on the other side, equals mg. Now, if I wanted to eliminate the n, I could solve for n out of 1, plug it into the other. It's a mess. We don't want to do it that way. It's so much easier if we just divide the two equations. If we divide these two equations, there is an n in all four terms. So you notice if I factored it out of these two and factored it out of these two, I could cancel them out. So I can just eliminate all the n's out of here. And so when I divide them. So here's that same thing with all the n's gone. Over here, I can cancel the m's and rewrite that. And so it's Vmax squared over GR. And now I just throw the GR up here and take the square root right here. So the maximum speed is now given by this right here. So there's the maximum speed that you can drive around a bank turn. Depends on the friction between the tires. It depends on the angle right there. Now, if you have bald tires, that is, if mu_s is 0, then we can just get rid of these two terms, and we just get GR sine over cosine, which is just GR tangent theta. So that's the maximum speed you can have if you have bald tires right here. Okay. Now, we could also say, what if you flatten down it? What if this thing doesn't have any bank to it? What if it's just going around a flat turn? Well, that means we could use this and we could plug in 0 for theta because you wouldn't be banked at all. If you plug in 0, the sine goes to 0, and this term goes to 0, and the cosine goes to 1, and that goes to 1. So the whole denominator is just 1. The whole numerator is just mu_s times GR, and that's where we get the maximum speed on a flat turn. That's the maximum speed you can go. Okay, and then the last one is, suppose you wanted to go around at an infinite speed. What angle do I need to bank it at to get an infinite speed? A lot of people think you have to bank it to 90 degrees. You don't have to bank it to 90 degrees. To make this infinite, all I need is the denominator to go to 0, because if the denominator is 0, you get infinity. So we'll just set cosine theta equal to mu_s sine theta. That's when you get V as cosine theta equals mu_s sine theta, or dividing that out, the tangent theta is just 1 over mu_s. So given a specific value of mu_s, this is the angle you'd have to be so you could ride around at infinite speed. So if mu_s were 1, 1 over 1 is 1, tangent of what is 1? That's 45 degrees. So if the mu_s is 1, you could go around this at an infinite speed at 45 degrees and not fly off. Okay, so that takes care of the maximum speed. Now if we look at the slowest speed I could go right here. Well, you don't have to work this problem out completely again, because when you're going the slowest possible speed, the only thing that changes is the friction. Now the car wants to slide this way. And so the friction fights the slippage, so the friction would be in that direction right there. So the only thing it does to this problem is it just changes the sign of that. Instead of pointing down this way, it's now pointing up in the other direction. And so this just becomes what? A minus right there. That just becomes a minus, which means that becomes a plus. And that's the only, and then down here, when you're on the verge of slipping, now the speed is a minimum because you want to slide down this way. So this would become a minimum. Okay, so the only difference is it changes the sign of this, makes this a minus, makes this a plus, and makes that a minimum. Okay, and so again, it changes the sign here, and makes that a minimum, which really, I just wrote it down here in red. This is the minimum speed that you can go around. And you can see that this is definitely smaller than this because the numerator, you're subtracting, which means you have a smaller numerator. The denominator is bigger, so this Vmin is definitely smaller than Vmax right there. Now, if we wanted to say what's the minimum speed that you could go if the tires were bald, again, you would let mu_s go to 0, these two go to 0, and you get GR tangent theta. You know, the maximum speed was also GR tangent theta. So if you had a bald tires on a bank turn, you better have a pretty good speedometer because you have no leeway in your speed. Your minimum maximum speed become the same value. If you have tread on the tires, that opens up and it gives you a bigger range of Vmin to Vmax. Now we can also say, can you stop right here? Can the Vmin be 0? Well, yes, as long as this, when this becomes 0, that means that gives you your Vmin. So if the numerator, if we set the numerator equal to 0, sine theta equals mu s cosine theta, that's what we're going to do right here. That's for Vmin equals 0. Well, then I just bring this down, and that gives me the tangent theta equals mu s. You notice this was the maximum speed. This was for the minimum speed right here. And so you notice if mu s is equal to 1, they both become the same. And so if mu s was 1 and this was at 45 degrees, you could go any speed from 0 to an infinite speed right there. Now, if we wanted to look at an anti-bank turn, instead of going around like this, you're kind of going around like this. You're going around like on the surface of a cone right here, which is much more dangerous right here. We don't bank turns downward when we go around them. We always bank them upward right here. But if you did want to figure it out, what your speed would be, all you'd have to do to be down here is change your thetas. This is positive theta to a negative theta. You notice for an anti-bank turn, this theta, sine of minus theta, you put a minus in front. This one you wouldn't do anything to. This one you change the sign of. This one you wouldn't do anything to. And that would be the maximum speed for an anti-bank turn. And since you're subtracting here, you're going to have to go a lot slower in an anti-bank turn. And I think for the minimum speed, there is no, there's only a maximum speed, so we don't even need to look at that one right there. So this is the bank turn problem. It's probably the most complicated circular motion problem, and it's actually the same as the problem we did before if you just took away the friction. That conical pendulum is just, we were calling that the tension, and we were calling that the weight. Every circular problem that you have to do on the homework is really this problem, but either with the friction equal to 0 or giving these guys different names right here. So they're all the same. Okay, so now you can work out every single problem in chapter 5. Okay, now that chapter 5 isn't due until, let me see, and that's going to give you actually 2 weeks after Monday right here. Remember, on Monday, you're taking the exam that covers chapters 1 through 3. Then chapter 4, which is the beginning chapter on forces, that's due a week after Monday. And this one here that's a little more involved is due 2 weeks after Monday. If you have any questions, either email me or or get in touch with Sarah. She can help you too. Okay, good luck on all this right here. And so hopefully we'll stay in touch. Bye.